Okay, I think enough people are here. I'm going to go ahead and get started now. Um, Welcome to Power Analysis Workshop. I probably should change that title. I like stole these slides from one we did 2 years ago and changed some of it. So we'll see how much I forgot. We'll see if there's anything in here that I should have changed, I didn't change. I am Danny Swan, which I'll talk about in a minute. I work for Smarter Consulting, which is a consulting unit inside the College of Education. Today we're going to talk about Smarter Consulting. I'm going to talk about what sort of power analysis is, and also about Monte Carlo simulations, because they're kind of an important part of doing more advanced power analysis in certain contexts. And we'll probably take a break after that for just a few minutes, and then I will go through some examples in G-Power and some SEM and actually a path analysis, power analysis in R using Lavon and SimSim. Lavon is structural equation modeling software, or a package really for R that lets you do a lot of the stuff you might do like in M+. Not everything you can do in M+, you can do in Lavon, but a lot of things you can do in M+, you can do in Lavon. And SimSim is a nice little package that sort of has got, like doing a simulation can be a really complex task that involves programming in R, but SimSim has automated some of that stuff specifically for SEM models. So we can use that to our advantage. Man, I should really capitalize that D. Statistics, Smarter Consulting stands for Statistics, Measurement, and Research Design Techniques in Education Research. Tasha Barefis is responsible for that name. I did not pick it. The director is Adam Sales. He is not here today. I am Danny Swan, like I said. Adam does consulting usually with staff or faculty who want to do do a grant proposal, and then you do power analysis and describe their design and their analysis model really well. So he will help with that and then sort of usually write himself into the grant for some money to pay for his position. I, on the other hand, do consulting with students, specifically students in the College of Education. I can also consult with non-College of Ed people if they are currently taking a stats class in the College of Ed, but only during that time, because people a lot of times ask their professors and they don't really want to do that. So I will do that for them since they're paying the College of Education to learn about stats. So I help for that for a little bit. I can help with just about anything, from sort of talking about your research questions and how you might approach that, to thinking about what analysis is appropriate, interpreting output, and I can also I can give help like writing code in R if you need to do an analysis that like SPSS doesn't cover very well. With everything but writing code in R, it's really about you coming to me with questions as opposed to like me, I'm not going to tell you how to write your results section for your dissertation or your, anything in particular. But if you have questions, you say like, I'm not sure how to talk about this particular result. I can give you help with that kind of stuff. And especially with qualifying processes, especially, I have to be a little more withholding because it's really a process for you to sort of show you can do research, and so I can give a little bit of help, but I have to be a little more careful about the level of help that I give with the qualifying process. Are there any questions about Smarter Consulting in general, what we do?
So if it just asks Adam's question.
I mean, if you think it's like a really simple question, I can probably answer it, but Adam.
I've worked with him on grants before.
Yeah, I mean, I would say if it's a granting question,
I know that, but like if it's just a quick question.
I would be happy to answer that question, I think. Yeah, I mean, I don't see why I couldn't. And also our emails are on the website. So like, I would always encourage, if you think it's a question that could be answered by email, to write us an email, write me an email. I would prefer actually the Smarter Consulting email address. I try to check regularly, but I sometimes forget for a few days. So if you want to answer swiftly, email the email that's my email or Adam's email that's on the website, and that will get you an answer more quickly. And if it's a question that turns out is not easy to answer in person, or sorry, over email, we'll say, hey, make an appointment. We'll talk about it in person. But it's never wrong to go to email first, because you maybe just really get you an answer much quicker than having to wait till like next week when there's a slot open. So that's always a good idea, is maybe if you think it's simple enough, send an email and we'll try and answer it by email. Anything else? Okay, so what is the point of power analysis? I think of it as having sort of two purposes. The first, most common one is determining the necessary sample size for an experiment to be effective prior to gathering data. And by effective, I mean if you get an effect of some treatment, some intervention that you think is big enough to be meaningful, right? Making sure that you get a sample that's big enough that you will probably get statistical significance in your analytic model for that meaningful effect size. And what meaningful means is going to depend a lot on your discipline and the context. And we'll talk about that again in a minute. But I see that typically in grant proposals, which I don't do much of. That's really Adam's job. But people come to talk to me a lot about dissertations and qualifying processes. And I think people think about the second one less, but I think it's actually important and useful more often for students than they realize. So in contexts where sample size is sort of outside of the researcher's control, if you do your analysis, because maybe your advisor has a data set that they gave you and you're doing a secondary analysis on it with what is available to you, and the sample size is a little bit constrained, and you do your analysis and you get a result that to you, like the effect you see seems significant, or not, I should say, seems meaningful, because significant is something else in this context that seems meaningful, but is not statistically significant. Depending, maybe it's only 40 students in this like secondary data set you're working on, and so maybe you just don't have the kind of power that you need to see a significant effect, and so you can actually do post hoc power analysis to get a sort of an empirical sense of what your power was, if assuming that effect that you see in your data is actually there in the population. And power analysis won't tell you that, but it will tell you, assuming that this effect is real, how much power did you have to find significance? That's what post hoc power analysis can do. And actually, I feel like a lot of people come to me want to do an a priori, like a before the analysis power analysis, and that is not super appropriate in a lot of cases for students, because they don't have any control over how many students they're going to get. And so really, sort of after the fact, if there's some issue in your analysis, after the fact can be more informative than trying to do it beforehand. So those are sort of the two contexts I think the power analysis is useful. There are some other things that G-Power does, and I'll go over them briefly, but these are the two that I see most often as being useful to students and maybe to faculty, but I don't interact with them as much. And I should say that what I am talking about today is very much focused on the kinds of questions that I get from students when they come to my consulting. Actually, I should say I am also a student. For those of you who don't know me, I'm a student of the Quantitative Methods program. I am ABD, so I'm proposing my dissertation right about now, but I've been here for a few years, so I know a few things. So I'm not going to talk about randomized control trials today, because in my experience, students don't want to do randomized control trials. I can help to some degree with randomized control trials, and if you want to know about randomized control trials, I have some materials from 2 years ago where we did talk about randomized control trials. So if you come at me later, and I'll send you an old PowerPoint that has some RCT stuff in it if you want it. But my experience is that students don't want to do RCTs, and if you're doing an RCT, you can afford to get somebody else to come in, like Adam, on your grant to help you out with that power analysis. So I don't necessarily see a lot of point in spending a lot of time on that specific software here. I also am not going to talk about hierarchical models. They do come up sometimes in people's QPs and dissertations, but it's like a whole other kettle of fish, and I sort of want to focus on some general stuff, and I can always help you with these power analyses later. So this is sort of to get you in the right space for thinking about the information that you need to do power analysis and sort of a general approach to it. And you can always ask me questions at a future date if you need more help. Okay, so power analysis review. So when we do a hypothesis test, there are 4 sort of possible outcomes. And this table, right, has this sort of the truth, right, the population level truth on the top, and sort of what we get from our statistic, our hypothesis test on the left side. So we never know what the truth in the population is, right? Because that's why we do statistics, because it's cheaper than polling every person in the whole world, or whatever our population is. So if if the HO hypothesis, the null hypothesis, right, that there is no effect is true, you can fail to reject the null, and that is a correct decision, right? Or you can have the null hypothesis be true, right, that there is no effect, and you get a significant effect, right? You say that there is a significant effect, that there really is a difference between two populations or whatever, and if you reject HO in that context, you have a type 1 error, right? That's the really bad one. The sort of still bad one, but maybe less bad one is, let's say that the null is false, and that like there actually is some difference between two populations that you're interested in, that your treatment has an effect in reality, right? In the population it would have an effect, but you're sort of doing it on your sample. Let's say that you fail to reject the null when the null is actually false. That's a type 2 error, which is still not great, right? It's less sort of, maybe depending on the context, less bad than making a type 1 error, less bad than saying there's a real difference when there isn't. Still not desirable. And then if we reject the null when the null is false, that's a correct decision as well. That's great. We love that. It means we were right in the first place. We're the smartest people in the world. That's the most beautiful one. So, we want to maximize our correct decisions, both fail to reject the null when the null is false, or sorry, fail to reject the null when the null is true, and reject the null when the null is false. And we want to minimize type 1 and type 2 errors. So power is related to making the correct decision. So power is the probability of making the correct decision given all the stuff, and I'll talk about what that stuff is in a minute, in our analysis. So the factors that influence power, the biggest one, right, when we do a prior power analysis before we gather any data, before we do any analysis, is our sample size, right? The larger the n we have, the more power we have to find a significant effect when one is present, or even when one's not present, to be honest. Sometimes this includes the number of groups, depending upon the analysis, and also the ratio of group sizes can matter. So like the most ideal scenario when you're comparing between multiple groups or two groups is to have like an exactly equal sample size in each of these groups. That sort of, you get the most power from every person in your sample when you have equal sample sizes. When you get unequal sample sizes, some of the people that are in the bigger one, they're not as good for your power as they would be if you had some people to match them in your other group. The magnitude of the true effect is very important in understanding power analysis. The tricky part about the magnitude of the true effect is that in many of the kinds of models that we're interested in, like a regression, the typical way that we express the magnitude of the true effect has to do with the proportion of variance explained in the outcome, and not about like the Hedges G or the standardized mean difference, the D, that you see in literature. So one of the tricky things about power analysis can actually be getting an effect size that is useful for doing your analysis in the first place. And I'll talk about how to kind of maybe use some other information to kind of get at that to the best of our ability. But the tricky thing about power analysis is to some degree it always involves guessing. Sometimes your guessing is very informed, sometimes your guessing is poorly informed. And I'll talk about that in a little bit. Your analytic model, your method, hypotheses tested, sort of what you use to analyze your data has an impact on your power, and also sort of how you approach power analysis. And also your chosen type 1 error rate is important. The lower your, like the higher your chance of making a type 1 error, the more power you have. But typically, we have very little control. Sorry, go ahead. So the more likely you are to make a type 1 error, the more likely you are to reject the null if the null is false. Really, the more liberal you are with your alpha, right? So if you go like 0.1 is your cutoff, right? That means in general you're more likely to reject the null, right? So by default, power is increased because whether or not the null is true, you're just more likely to reject it when you increase your alpha level. And so, like if you go to 0.01 from 0.05, you've reduced your power. You made it harder to reject the null, and that's independent of whether or not the null is true. Does that make sense? Okay. Any questions about sort of this piece? I know I talked in very broad generalities, but it's sort of the best I can do because power is a little weird. Yeah.
we going to talk about oversampling at all?
Like for populations that are small?
No, like oversampling in a way that like increases your time.
No, I'm talking broad generalities today. Sorry. I actually don't know. I'll be real with you. I don't know a lot about oversampling. So I could learn about it, but I couldn't speak to it to you this very moment. Okay. So the tricky thing about power analysis, right, is we have very little control. Type 1 error rate is usually set, right? 0.05 is the big one, but sort of on a field by field basis, on a journal by journal basis, you have very little control over what the like approved p-value you have to get less than to be significant, right? 0.05 is the big one, so like that's set. If you're doing an a priori power analysis, right, where you've got to, like, you're trying to fund a grant, sort of do your qualifying process, your dissertation, the 80% power is like typical, like it's the cutoff that everybody wants. If you're doing a post hoc power analysis right after the fact, your sample size was probably limited in the first place. You had no control over how many people you gathered data on. And if you don't have control over how many people you're gathering data on, there's no point in doing an a priori power analysis, because you can't. If you have 80 people and your a priori power analysis says you need 120, you can't do anything about it. So you have very little control. The number of groups, when it matters, is typically dictated by the experiment, right? So you have control and maybe a treatment or 2 treatments or 3 treatments, right? The number of groups you have, can't change that. And typically the analytic method, like the model you use, is dictated by the experiment or the questions being asked, to some degree by the structure of the data as well. But these many of the features that impact power, you don't have a lot of control over. So you're either trying to find the right number to get people to gather data from, given a bunch of constraints that you already have, or trying to understand how much power you had, given things that you had no control over in the first place. That's sort of the bad news about power analysis. Like I said, the magnitude of an effect is a tricky one. So many people that come to me are using regression-based approaches, right? And they want to figure out how many people they need to get data from. But the effect size used for power analysis for regressions is this. It's actually not F squared, it's F. That's wrong. It's just F. F squared is something else. And F is related to the proportion of variance explained. It's like the variant. It is the ratio of the unique variance explained by your predictor, let's say your treatment, over the unexplained variability in the outcome, which is, I know, a weird measure, something that's not necessarily super intuitive. And if you have R squareds from your models reported in literature, it can be really easy to get this calculation. You can actually, G-Power has a little box you can like put your R squared for your effect, your factor, your treatment in one box, the error R in the other box, and it'll just like figure it out for you. But I think typically people don't report R squareds in the literature. That's not really, they might report their model and all the betas and the standard errors, but they don't report the R squareds for the effects and the unexplained variability. You can also go to these like suggested guidelines, which is where a small f is 0.02, a medium f is 0.15, and a large f is 0.35. And Cohen's got a bunch of these guidelines for all the different effect sizes. I don't like them. I don't think they mean anything, because what a small, medium, and large effect means is something really different depending on the context. So the classic example is this Rosenau and Rosenthal, 1989, which was a study about the effect of taking a small dose of aspirin on heart attacks. And sort of partway through this study, they did like a sort of an analysis of the data that they had gotten so far, and it showed that there was like 0.12% of the variance in heart attacks was explained by taking this aspirin, right? And so really what it meant is taking aspirin reduced your chance of heart attack by like 0.1%, right? But that was so big in the context of this experiment that it was considered unethical for them to proceed with this experiment and not give the control group the aspirin. And so they stopped. They told everyone in the control group, you should take aspirin, and that was it. They were done. And so how much variance explained, what a meaningful effect is highly variable, highly contextual. So that's a thing you have to sort of decide for yourself. We can make some educated guesses with bivariate correlations about what these different proportions of variance explained are, but it can be tough to do well. And I think I just realized I may have made a mistake in my example. We'll see what happens. Okay, so this is sort of a very abstract example. So let's imagine that Y is some outcome we're interested in. Let's say, anybody have something they really care about, some outcome they're really interested in that I could just make up a story about real quick? Anybody? Let's say Y is depression, like some depression scale that you've got. X1 is this treatment you're interested in, and X2 is their anxiety, some anxiety pre-measure before the outcome. So Y is like depression after this treatment. X1 is whether or not they got the treatment, and X2 is their anxiety at the beginning of the treatment. And if you imagine each of these circles is the variability, the total variability in Y, total variability in X1, total variability in X2. So like this Y, right? That's all the variability in Y, all the variability in X2, all the variability in X1, X2. And these overlaps, right? This is the variability shared by Y and X1 that they don't share anything with X2. This is the variability that Y and X1 share together. They don't share with X2. This is the variability that treatment and anxiety share together right here, but they don't share with Y. And this is the variability that all three of them share. And so you can imagine that this correlation, this whole piece right here, right, this chunk that that depression and anxiety share, plus this chunk that is shared with treatment and anxiety, right? This whole thing is the correlation between depression and anxiety, and this whole thing is the correlation between sort of depression and treatment effect. Yeah, and this whole thing is the variability that is shared with between the treatment effect and anxiety, right? And so when we do power analysis, we really want these chunks, this like unique effect, this unique effect. We don't care as much about this unique effect, but it can be helpful to think about that. And we also need to think about the proportion that's unexplained by anything in our model. And this down here, let's imagine these are actually the squared correlations. So they represent the proportion of variability that's shared by these two things, that they sort of the amount that they vary together. This is some weird math. There's sort of an example of how we can think about bivariate correlations to sort of get at pieces we're interested in. So let me back up a little bit. The context for this is often, like I said, people come to me and they want to do a regression power analysis, and they don't have shared variability, but they do have lots of examples of like correlation matrices, right? So you can get at the correlation between two things, and by sort of thinking about the correlation between the sort of the correlation of these three things with each other one at a time. So if you have three things, there are three correlations between those three things. We can sort of figure out like the upper bound on how much things share and the lower bound on how much things share, and sort of kind of make some choices or really do power analysis across all these bounds. And so, okay, I'll talk about this for a second. So so here in this bottom corner, right, I've got this. So Y and X1, 20% of their variability is shared. They vary together 20% of the time. Y and X2 vary together 15% of the time. And X1 and X2 vary together also 15% of the time. So if we have a model where depression is predicted by this treatment effect and anxiety, the most variability that can be explained in Y is 35%. So it's that 20% from the treatment effect and 15% from anxiety. And that's assuming that this little bit in the middle doesn't exist, right? None of the variability in depression that is explained by the treatment effect has anything to do with the variability in depression that is explained by anxiety. but it could be as low as 20%, because it could be that all of the variability that's explained by anxiety and depression together is actually inside of that variability that's explained by the treatment effect and depression. And so really none of the variability explained by anxiety is unique, right? It's something that they share, that the treatment, anxiety, and depression all share together. And you have no way of knowing that because you're only looking at how much two things vary together when you look at a bivariate correlation. Is this making sense? It's the first time I tried to explain it this way. Yeah.
Sorry, why is it the lowest amount? Why is the lowest amount 20% and not 15%?
Because if you're using both x1 and x2 to explain y, right, you know that 20% is definitely going to be explained. That treatment effect, at minimum, right, you're going to explain 20% of the variability because, go ahead.
Do you just kind of take the highest?
You take the highest of any of them because the thing is that, like, if you're imagining a disproportion, right, 0 to 1, right, or 0 to 100, 20% is definitely explained because that x1, that treatment effect, explains 20%. And so even if they're like, if this x1 and x2, if you imagine they like collapse across each other and they're just like two circles together overlapping with depression, you'd still have 20% explained no matter what. Like you have a little bit that the treatment was explaining by itself without anxiety, but anxiety couldn't eclipse the amount explained by treatment. Does that make sense? No, it's the biggest number. Yeah, single number. That is a typo. No, it's not a typo. Okay. Or no, it's okay. Sorry. So the next bracket, the unique variability explained by x1 and y is at most 20% and at least 5%, right? So it could explain 20% unique variability, right? It could be that this treatment and anxiety don't overlap at all, right? And 20% of the variability in this outcome is explained by treatment, but it could be again that they overlapped completely, and so only 5% of the variability is just due to this treatment effect. And similarly, this next bracket should be about x2, not x1. So the total unique variability explained by x2 and y is at most 15%, right? So it could be all the variability in y explained, all the variability in depression explained by anxiety is unique to anxiety, or it could be that none of it is because it's all caught up in the amount that's shared by anxiety and the treatment effect. So we can make guesses about the overlapping proportions to arrive at something like F, but it will be a guess, sort of in general. So the best case for F, I keep saying F2, but it should just be F. The best case for X1 is about a 0.31, which is a pretty large F, and the worst case is a 0.07, which is a very different power. And this is like kind of our best case, right? Where X1 and X2 only explain unique variability, right? Best case in the sense that like you're sort of imagining all the variability that you know is captured by the treatment and captured by anxiety is unique to it, and so you can say like it's got a really big effect size, and it's you're more likely to get it's easier to get the power you need. But if you're wrong about this, if you imagine this scenario, right, but really the unique effect sizes are smaller, and this will become, I think, more concrete when we talk about power analysis and G power. But the sort of if you say that it's going to be big, right, the effect is going to be big, and it's really small, but still small enough that you care about, and you've powered for that big scenario, yeah. So 0.31 would be 0.2 divided by 0.65, I think. Yeah. So again, it's the proportion of it. So if in the best possible scenario, right, that they're not shared by each other, we've got this 35% of the variability is explained in Y, which means that 65% of it is unexplained, right? And then X1 we'll say is actually 20% of the unique variance is explained by X1. So if you divide 20 by 65, you get 0.31. That's a great question. And the worst case, right, is that actually there's only 20% of the variance is explained in y, and so 80% of it's unexplained, and the unique variability is only 0.05. So 0.05 divided by 0.8 is like, or 5 divided by 8 is like 7%. That's wrong. Maybe it's actually like, well, anyway, in this like worst case scenario, it's going to be much smaller. So you're sort of, the point of this is to recognize that although we can make educated guesses based on bivariate correlations and sort of other things, you're still guessing. And this is sort of our best case, right? But it's best case in the sense that like it is the best for like not having to get a big sample. So you can make an argument for a smaller sample, but like if you're wrong and the effects are much smaller than what you predicted, then you may not have gotten enough data to show significance, and you just wasted a bunch of time, possibly a bunch of money. So when powering, you want to power for your minimum meaningful effect size. So what effect size, what proportion of the variability in your outcome would you have to be explained just by your treatment, just by your sort of the thing you're interested in for you to care about it, right? Not just what do you expect, but how small could it be, and you still care. You still want to find significance, right? Because I think sometimes people come to talk to me about their power, about interpreting their output, right? And they're really lucky they get like 1,000 people in their data set, right? And they get this tiny effect, right? It might be like 0.1% of the variability is explained. And they're like, okay, so how do I talk about this? And I go, well, hang on. Do you care about this? Like, is this worth teachers or practitioners or school districts or whatever? Is it worth a bunch of time and money to implement this intervention when you're only moving this outcome by a tiny bit, even if it's significant? Is it meaningful, right? So think about what are the costs to the people that are doing these interventions, right? How hard is it to implement? How much money does it cost? How difficult is it for the student or the person you're treating? How small can you go and still be meaningful? And also the smallest effect size in your model. So like in a ANOVA context, if you've got like a treatment A and then sort of like two different contexts. So like maybe you've got some sort of treatment like I talked about where you're trying to treat depression, and there's like an in-home version and a like in the like office of the therapist version. And so you've got this sort of effect of being at home or in the office, and this treatment or like business as usual, right? So we call it like an A and a B factor. And then there can be an interaction effect, right? So the specific effect of getting the new treatment at home versus the old treatment in the office, right? And a lot of times these interaction effects are sort of the most interesting effects, the things you really care about, but they're much smaller. And so there's sometimes, maybe not so much anymore, but there's been an unfortunate tendency in the past to power for these main effects, right? And if you're powering for the main effects, but the interactions are much smaller and you really care about them, you could easily underpower for your interactions. So you really want to think about not just what's the minimum meaningful effect, but what is the smallest effect in your model going to be, right? What is the smallest effect that you might care about in these interaction effects? Because you really got to power for the smallest, the sort of least effective, the least sort of, the smallest meaningful effect, really. Like, it's important to think about that. And as a caution, but also kind of a bonus, nothing I talked about included covariates, right? So maybe you want to control for age and gender and a bunch of other stuff. And so, like, the degree to which they like overlap with these other pieces can be difficult to think about, but also they probably explain some variability in your outcome in your depression that's unrelated to your treatment, unrelated to anxiety, right? And so again, if you remember that ratio is the unique variance explained by the thing you care about divided by the unexplained variance. And so if you can explain some of the variability in the outcome using these demographic pieces, that can increase your effect size in the context of regression specifically. Like, it doesn't change like a standardized mean difference, hedges G, hedges D, but in this context we care about in regression, that reducing the amount of unexplained variability just makes your estimates more precise, gives you more power. So before I talk about Monte Carlo simulations, I know that I'm talking about this in broad terms, but are there questions about what I have sort of talked about? The other thing, so trying to think about the pieces you need, and it'll be more specific again when we talk about G-power in a little bit. But the other thing is a lot of times people come to me to talk about they're interested in some research that has been done in one population, they want to do it in a different population. And they say, well, I don't know what's going to, I don't know how this is going to turn out with this sort of different separate population. And what I say is look at the research that's been done on these other populations, right? To the degree that like the effect on college students is like going to be like the effect of middle-aged people working in an office, right? You can make some guesses about how much, how like the college students are going to be, right? That they can at least give you some sense of the proportion of variability explained in executives, and you can sort of use the literature and the theory to the best of your ability to talk about, whether these effects are going to be smaller or bigger. Ultimately, power analysis is really about making an argument for why your guesses are reasonable. And so, if you're in a new field, you look for parallel research to the best of your ability. And without I don't have a good concrete example because everybody's going to be doing a different question. But if you can't find the answers you want in your specific thing, look for stuff that's very close and that can give you a parallel sense of what would be happening in your sample. And then just be conservative, right? Be on the small end of what the magnitude of the effect might be. Okay, now are there any questions of what I talked about?
Can you repeat again how you got
this math?
The math.
Yeah. Well, so let me just say, if you've got this stuff, I or Adam can help you think about it. So, but I mean, what I've done is, so the best case scenario looks kind of like this, where there's no overlap in that middle between y and x1 and y and x2. The three of them don't covary any amount at all together, right? So and so in that case, this overlap, that middle piece is 0, which means that this proportion of variance explained by y and x1 is just that little ellipse there, and x1 and x2 is that little ellipse there, and y and x2 is that little ellipse there. And so you can say, okay, well that's there's 20% explained by x1, 15% is explained by x2. Together they explain 35% of the variability in the outcome. And so that's your best case scenario because only 65% of the variability is unexplained in y.
Okay, so I get the 35.
All right, that's sort of the top part. Now, the denominator is the unexplained variability. So 0.35. Well, no, because so the numerator is the specific effect. So the numerator is going to be the unique variability. Whatever is in this piece right here. Yeah. So it could, if it's like this, it's 0.2. If it looks like this, where there's some overlap, it's something less than 0.2. And it could be all of that 0.15 explained by x2 less than 0.2. So it could be as low as 0.05 as the sort of unique piece that's right here. But it could be anywhere from 0.05 to just a little bit less than 0.2, and you don't know. And that's sort of the unknown tricky piece, right? And so you have to make your best guess. Or one option is also to do a range of values and see how much the different and report a range, or sort of say we don't think it's this low, but it could be this low. Just sort of to use your best judgment in conversation with somebody like me, hopefully, to talk about to be as principled as possible, right? It is a little bit of a game, right? You're trying to get this granting agency to give you money, but obviously you don't want to overstate and then get nothing, and then you look like an idiot. You look like an idiot. You look like a jerk who just got money for no reason. So it's definitely a little bit of doing your best to be both principled and also realistic about how many people you can get.
I understand conceptually now, but I'm trying to put notes because I know later I'm going to do
right. Well, I think maybe when we get to G-power in a little bit,
and it'll answer it.
It'll sort of get more concrete, and then we can. And there's time at the end of this that I don't have structured, so we can have all sorts of question and answer time at that point. All right. So we'll talk about Monte Carlo simulation sort of in the abstract a little bit. So there's other things like regression, t-tests, stuff like that we'll talk about with G-power. We arrive at those power calculations analytically. So what that means is there are these math formulas that we know how regression and all this stuff works, and we can use those to arrive at solutions for the power in a regression or a t-test. With more complex models like SEM or path analysis, and sometimes hierarchical models, although there are pieces of software that'll do like HLM power analyses for you. But depending on how complex you get, it may be that nobody's done the work to get that to work for you. But definitely for SEM or path analysis, the math underlying them isn't like tractable, is what it's called, where we can't really get there's no like simple generic method that'll work for like every possible model, and so we sort of have to use Monte Carlo simulation to arrive at power. And so what a Monte Carlo simulation is an attempt to use something empirical, something observable, to arrive at properties of it. So if we want to know about coin flips, for instance, so imagine a fair coin, you have a chance of, say its probability of getting heads is 0.5, right? We call heads a 1 and tails is a 0. So if you get heads, you've succeeded. If you get tails, you failed. We know, because of the Bernoulli distribution, which is what models this kind of behavior, that the mean would be 0.5 and the standard deviation would be also about 0.5. But let's say we didn't know that, right? And you just wanted to know the mean of this coin flip and the standard deviation of this coin flip. You could actually flip a coin 1,000 times, record all those thousand times as ones and zeros, take the average of the ones and zeros, take the standard deviation of the ones and zeros, and arrive at sort of an empirical mean and standard deviation, and also a distribution of coins, which would really just look like two bars that are like exactly the same height, close to, right? So a Monte Carlo coin flip, a Monte Carlo simulation is about having some population model. In this case, your population model is nice because it's a coin flip. You just do it, and then using like a set number of samples, a large number of samples, right? Each coin flip is one sample, to arrive at knowledge about what how good the statistic, this mean and the standard deviation actually is. And so let's say we have a model-based example. So we're going to generate a sample of data according to some population model. So let's say this population model is a regression, where really all you're doing is you've got y is equal to some intercept plus a treatment effect and error. That's your population model. This error, this E, is usually like normally distributed with a mean of 0 and some variance, but it's just like there's just some noise, right? So there's like each person is the effect of not being treated plus whether or not they were treated, and then some deviation from the mean. And we can generate we can say this is y is equal to the average if you weren't treated, and if you were treated you get a 1, and you get some D. If you weren't treated you get a 0, and you don't get that D effect, and you get some error. And so we get 50 people from not treated and 50 people that were treated from this model. So really it's very simple. You either were treated, you weren't treated, and you get, you have a little bit of error. And you apply a regression, right? And the difference between the regression and this population models, you don't have that error in the regression. You're not getting that error, but you are getting some estimate of B and some estimate of D. The little d is an estimate of the treatment effect. So you get a sample of 100, half of them are untreated, half of them are treated. And this is a computer simulation. This is like a computer just says we'll say that your mean if you're untreated is 5 in the population, and your mean if you are treated is an additional 5. So it's 5 if you're untreated, 10 if you are treated, plus some error that's due to your personal differences, right? So I'm a little more depressed than she is. That's about me, not about this population model. And so we get this regression. We get an estimate of the mean and an estimate of the treatment effect. And so D is an estimate of D. The little d is an estimate of big D, and little d is an estimate of this true population thing. So if we do steps 1 and 2 many times, so we draw, get 100 people, 50 of who weren't treated, 50 of who were. We get the treatment effect, and we do that 1,000 times, and then calculate the mean of those 1,000 treatment effects, we have the difference between that empirical D, that population that we started from, and the average of these treatment effects is going to give us information about how well the method performs, which includes power. So if for each of these Ds, these little Ds, you test whether or not it's significantly different from 0, and then you take the proportion. I think I talked about this. Yeah, okay. So we estimate a P for each D, right? So the P is the probability of it being true under the null hypothesis, right? So if P for a given model is less than 0.05, great. If it's not, that's bad, right? Because the truth that this is a probability model. This is like an experiment in our heads. The truth is that there really is a difference. There really is a treatment effect. And I'm going to talk about this again before I do power analysis method Monte Carlo simulation. So don't worry. And it's actually, I'm going to use somebody else's explanation. So my explanation sucks. We'll hope that this other explanation is better for you guys. But assume we generate 1,000 samples. And for 834 of those samples, there was a true effect. That means that there's about 83% power for this model that we've sort of said might be the truth. And we can use computers to play around at maybe we got 100 here. We don't need 100. We need something less than 100 because we've got a little more power than 0.8. And so we can sort of go lower to get a better sense of what it's at. This is a very generic example. And I'm going to talk about it twice because it's not the most intuitive thing. I think if you have questions, let's hold until I do the second example because it's a little more complete and it might be more straightforward. At this, yes?
This is a new example, right? So this P isn't the probability of the point.
No. This is this P is the probability of the probability of existing under a null hypothesis, right? A p-value like when we do a statistical test. So if you're less than 0.05, it's significant. If you're greater than 0.05, you're not significant, right? And so we've got this true model, right? Where this D really does exist. We know that it actually exists because we're saying that the world is really simple. That you've got an effect if you're not treated, and you've got an effect if you are treated. And so the population of treated people are actually different than the untreated people for real in this imaginary situation. And so each of these samples will be more or less close to the truth just by sampling variability, like we have in the real world. And this is, by the way, how all statistics works. This is where the underlying assumption is that if you do a statistic 1,000 times in the same way, right, that 0.05, that alpha level is 5% of the time. When you do this in this infinite number of times, or this very large number of times, you will, even if there's no difference, you'll say that there's a difference when there's not one. And we use this sort of large sample idea about statistics to get at some truths. But again, I will talk about this in more detail when we get to the example of Monte Carlo. So I think hopefully let this sit for a little bit, and we'll come back around to it, and hopefully it'll make more sense in 30 minutes or something. Right. So we'll just in this case, we'll say 134 of the 1,000 samples of 100 had significance, right? And so it's a rough estimate. In general, we're going to imagine about 83% of the time it will be significant if that D really exists. And you have to assess a range of models because you may need to specify strengths of relationships that aren't really important to your primary hypothesis when we think about SEM and path analysis. And we'll talk about this more in a little bit. And so you can examine a range of values to be, if you're uncertain about specifics, especially stuff that you don't care that much about necessarily. So in thinking about power analysis, there are a lot of options. I'm going to talk about G-Power today. I'm also going to talk about SimSim. I focused on them because they're free and they do a lot of things that people ask me to do. There's also PowerUp, which is this Excel-based power analysis. It's good for RCTs if you're interested in doing a randomized control trial. It'll do some of the stuff that G-Power does as well. Optimal Design is a Windows-only piece of software. It's also good for randomized control trials. I don't use it very often because it's even more opaque than G-Power is in some ways. But it is used by people to get RCT power analysis. M+ does power analysis. Does Monte Carlo simulations like SimSim does. And it does more stuff than SimSim will do. I sort of imagine that most of you are not going to do like really complex, weird, the kind of models that M+ does and SimSim won't do are, I think hopefully none of you are want to do that kind of thing. And if you do, well, then get M+, but it's going to cost you money. And then there's this thing called PASS, which I have no experience with. I've just looked around. People do talk about it. I know that it does power analysis. It costs money as well, but it is an option. So we're at the examples. Let's just take a little bit of time for a break. Let's come back at, let's say, 10 after 2:10 and get started. If you want to follow along in the G-Power software and you haven't managed to get it installed or confused, let me know. I'm gonna go to the bathroom real quick and then I'll come back and I can help you get it installed. Here are sort of one-on-one questions. We can use this time to knock that out. But otherwise, just get up, stretch your legs, think about something other than my bad Monte Carlo example, and we'll come to another one in a minute. So that's the whole thing for now. So see you in 15.